So today I'm going to be talking about one of my PhD topics, which was to look into the 2015 Nepal Gorkha earthquake. And I did that by studying earthquake sequence simulations. So sort of trying to understand what is the role of structural complexity in the MHD seismic cycle. So during the past 50 to 60 million years, the Indian plate has been gradually colliding with the Eurasian plate, closing the Tethys Sea, which once separated these two continents, and uplifting the Himalayan mountain ranges to about 5 to 8 kilometers above the Earth's surface. And the convergence between these two tectonic plates has been accommodated by crustal shortening and thickening along these megathrusts, which form these really extensive seismogenic zones, which host some of the Earth's largest earthquakes. So to give you a short introduction into this Himalayan architecture and the main Himalayan thrust fault, this Himalayan architecture consists of three distinct geological belts. Yeah, so there we have the greater Himalayas, the lesser Himalayas, and the sub-Himalayas, and all of these consist of sediments that were scraped off from this downgoing Indian lithosphere. And all of these geological belts are bounded by forward propagating sequence of thrust faults, namely the MCT, which is the oldest in the system, called the main central thrust. And then we have the MBT, which is the main boundary thrust, and the frontal most or the southernmost fault is the MFT, which is in red here, main frontal thrust. And all of these play faults merge at depth with the main Himalayan thrust fault, MHT. And this accommodates most of the crustal shortening and intense deformation. This was supposed to be an animation, but we had some issues. So this is a PDF document, so the animation won't work. But if it works, what it would show you is the general process of strain buildup and release associated with the large megathrust earthquakes that you have along the Himalayan front. So what happens is during the interseismic period, the shallow region here, maybe I should use that, that's better. Yeah, so the shallow region is locked, so or it's stuck together, while the deeper regions are slipping freely. So the shallow region where it's locked is where the plates are basically stuck to each other, and the lower plate is pulling underneath this higher plate, and so there's land subsidence. And then the stress builds up until it can't take anymore, and then the upper plate breaks free and springs back, causing this Himalayan wedge to sort of pop back up and creating these earthquakes, and also all the associated hazards like landslides, liquefaction, etc. So the MHT itself exhibits both along strike and down dip segmentation. So if you see from paleoseismic studies and a lot of historical data, there has been these megathrust spanning ruptures, which is the full true going ruptures like the 1934 Nepal Bihar earthquake and the 1505 earthquake west of this region. But there are also these blind ruptures which happen in the deeper sections of the fault, which only break small sections of the fault. And the examples are 1833 event and the most recent 2050 event that we're going to talk about. Now, it's very important to understand what determines the spatial extent of these seismic ruptures, because we want to put realistic bounds on the seismic hazards in this region. So, and the most recent event, like I said, was the 2015 earthquake. It was a magnitude 7.8 earthquake, which unzipped the lower locked edge of the MHT in central Nepal. It happened about it's a 50-kilometer wide segment, and it's about 70 kilometers from Kathmandu. And it destroyed a lot of old historical buildings, like you see here in these pictures. It caused about 9,000 deaths. There were like 500,000 houses that were destroyed, rendering millions of people homeless. So this was a fairly small earthquake, because it's not the huge earthquake that was expected for this region, but it still devastated Nepal. And if you were in EOS section C around 2015, 2016, which was when I was working, and if you ever walked in the corridors or went into the pantry, I'm 100% sure there'll be at least 2 people talking about some of these questions. Like every time I walk into the pantry or in the corridor, people were all discussing about this 2015 event. And the reason for this really animated discussions was because everybody was surprised why this earthquake didn't cascade into this huge event that they were anticipating. Now, why were they anticipating this big earthquake? Now, if you see from this, it's actually in between, it's a region in between 2 historical earthquakes. So you have the 1934 on the east and 1505 on the west. But this region in central Nepal hasn't had an earthquake in the last 500 or more years. So people and people who are studying coupling and other geodetic studies were pretty sure that the full fault is locked up to about 15 kilometers depth. So people were like very sure that there's a lot of slip deficit here, around 10 meters of slip deficit that has accumulated in this region. So they were expecting this huge magnitude 9-ish earthquake. But then this was a 7.8 earthquake that was only a partial rupture. So people always wanted to know why this earthquake did not cascade into this big event. And another question that was in everybody's mind, obviously, was what's next? The loading from this 2015 earthquake and all the post-seismic creep that followed in the deeper sections of the fault, what is it doing to the shallower sections? So the people were like wondering what next for this region. Which comes to some of the questions that we try to answer, hope to answer from this study. So one is, what controls earthquake segmentation? So why did this earthquake stop in the middle of the seismogenic zone, even though the entire fault is fully locked? And what is the role of fault bends in the seismic cycle? So specifically, the question that we want to answer is, what fault geometry best explains this Gorkha coseismic rupture and the post-seismic behavior? And of course, the next important question is, what are the future seismic hazards in this region? Now, determining the precise fault geometry is very essential to understand fault behavior, right? So, but the one thing that we know about MHT fault behavior is for sure is that it's not planar. And how do we know that? We know that from surface geology, seismicity, topography. To me, the most important piece of evidence comes from this, from surface geology, which is this huge long-term structure called the Gorkha Pakora anticlinorium. This is a huge anticlinorium in the middle of this Gorkha coseismic rupture. And if you really want to explain the existence of this structure, you need to have a flat ramp geometry that actually builds this topography on the surface. So most of the cross sections coming out of this region always includes this mid-crustal ramp, which coincides with the position of the GPA. But despite this overall similarity in these different fault geometry models, there were always the questions about, what is the location, precise location and depth of this ramp? Or are there more ramps? Are there other ramps? So it was, it's quite, like people are still debating about the MHT fault geometry. So what I really wanted to do was sort of take 2 n-member geometry models and sort of ask the question of which one explains better the Gorkha coseismic behavior. So the first model that I looked at was, I call it model E because it was a study published by Elliott and others, a 2016 paper, and it uses coseismic geodetic data and using fault geometry based on what is known about the fault geometry at depth. So it has 3 segments. The first is a 30 degrees north tipping ramp, and then that's followed by this flat portion. And then there is a steep mid-crustal ramp. And so there is a lot of evidence, like I said, about the flat ramp, flat geometry in the mid-crustal regions here to create the GPA. And so this geometry sort of makes sense. And it has been widely accepted as a MHD fault geometry. But there is also another model which came up, and I'm sure all of you are very familiar with it because it's from Judith's cross sections. This is a geologically informed model of the MHD, which is consistent again with Gorkha's coseismic data and the surface geology. So Judith and her group built this very comprehensive structural cross-section based on kinematic fault band fold model. And this incorporates a very detailed surface geology that they mapped. And this one includes a ramp in the middle of the seismogenic zone. Now, this ramp is basically required by the stratigraphy that is exposed in the hanging walls of MBT and MFT. So we have two now N-member models. They have roughly same features in the sense of it has the ramp flat ramp geometry to create these the Gorkha Pokhara anticlinorium, but there's also a middle ramp in this one which the other model lacks. So what I did was I fixed these two geometries and sort of ran numerical simulations, so earthquake sequence simulations based on the rate and state friction framework. I used the multiplicator form of this framework devised by Sylvain Barbeau, and this is basically it's very similar to the traditional framework, but here the fault strength depends on the area of contacts that bear the normal and the shear loads. So to sort of quickly tell you what it entails, you have two different geometries which are slightly similar, just the differences in the inclusion of middle ramp here. The red and the blue regions are the velocity weakening regions of these two fault structures, and the black lines are the velocity strengthening regions. And I've sort of marked the transition zone around 15 kilometers depth, and that's because that's where the microseismicity is generally observed in this region. So that's the depth we expect that it changes, the friction changes from a velocity strengthening to velocity weakening. And then what we did was we basically ran a suite of models by changing the frictional parameters for both of these geometry models. So on the left there, you have the one model H, that's the one that has the middle ramp. And the one on the right is model E, which without the middle ramp. And you can see this is basically an exercise to sort of start off with very simple cases where you have stable fault slip because your nucleation size is so large, you're not able to create instabilities. So you're going to have stable fault slip. And then you slowly start increasing the RU number, which is basically a non-dimensional number in this framework. So rate and state friction framework has a lot of different parameters that you can change. So you don't want to be caught up in this huge parameter space and sort of don't know what you have changed and what you're getting back. So when you use these non-dimensional parameters, what you can do is you can expect behavior like the complexity of the ruptures to increase as you increase this this ratio between the seismogenic width, which is basically the width of the velocity weakening region, and the nucleation size. H star is the nucleation size. So what we see is we sort of see these self-emergent partial ruptures that develop as the complexity increases, basically from stable slip to periodic through-going ruptures to partial ruptures that happen. But you can see from these simulations that you get partial ruptures as quickly as number 6 when we change the RU number for H, but it reaches up to about 20 when it's the one without the middle ramp. So fault bands in the middle of the seismogenic zone are basically creating these rupture segmentation for lower values of RU already. And another parameter is basically we change the ratio of static and dynamic stress drops. I have to tell this is a quasi-dynamic model, so we actually don't have the seismic waves. So it's radiation damping, but still what we do is we sort of control the nucleation style by changing this non-dimensional parameter RB. And again, we see a lot of persistent seismicity that is associated with fault bends with both models, because both models have fault bends in them. So what we did was, from all these different simulations that I ran, I basically picked only ones that have in them Gorkha-like ruptures. So basically, I looked at the surface slip distribution and the fault slip distribution and compared it against the Gorkha coseismic data that we have, and sort of selected only the ones that had in them these Gorkha-like ruptures. So basically, I compared it with geodetic data. In this, you have both the INSAR, so you have the ALOS scenes from, the INSAR scenes from ALO satellite, which shows the subsidence and the uplift subsidence in the high Himalayan region and the uplift of the Kathmandu Valley. So these two lower panels are basically the INSAR line of sight displacement. So the red one is the data, and the black dashed and solid lines are basically from my models. And you can see that they agree quite well, and both of these are agreeing quite well. So coseismic geodetic data with or without the middle ramp sort of agrees with the geodetic data. So INSAR data, and the same for GNSS data too. All these red ones are basically far field stations. So I want to remind you here that the slip happened 10 to 12 kilometers depth. So the slip was really buried. So if you're far away from the coseismic region, these stations are not going to see any coseismic data. So, but these blue near field stations sort of captured the slip, and you can see the black lines again, which are from my model, agrees quite well. And this lower right box is basically the fault slip distributions got from these respective geometries. And again, it's pretty neat. It's agreeing. So basically, we're able to get coseismic. We are able to fit coseismic data with our models pretty well. So I'm going to sort of go slightly deeper and show you how that cycle looked like. And in this figure, what I'm showing is on the x-axis is the time index. So you can't think of it as time itself. So it's not uniformly spaced. So when you see an earthquake, which is in red colors, it means it has very fine resolution. But when you see these darker colors, it's interseismic period, and it has more coarser resolution. And on the y-axis is the down dip distance, and color is the fault slip velocity. So, and what the first thing that catches your eye, of course, is that the interseismic region is the shallow region is completely locked during the interseismic period. And all of the ruptures are starting from the down dip area, right? All the small partial ruptures as well as the big megathrust ruptures are all originating from the down dip region. Now, this region is an area of high stress concentration because it's at the transition zone from velocity strengthening to weakening, and B, it also has the mid-crustal ramp. So you have changes in fault geometry here because it comes from a flat region to a steeper region and then moves on to a flat region. So this basically entails a lot of stress accumulation. So to help you visualize that, I've plotted the shear stress on the fault for 5,000 years, which is the x-axis is the years and y-axis is the down dip distance. The colors are the shear stress. So when you see these red colors, it means there's very high interseismic stress, and light to dark blue are regions of low stress. So you can see that this region down at the transition zone, it's always loaded. It's continuous loading from interseismic stress accumulation. And you also see that a previous rupture leaves this stress residual. Now, this is what creates this sort of segmentation process, because you're creating a non-uniform pre-stress on the fault, and you're sort of having these residuals from previous earthquakes, which then accumulate. After a few partial ruptures, the entire fault is ready to break in the next big rupture. And this is a way to basically visualize the same information, but I've plotted the earthquakes on the geometry. So now you can see that this one doesn't have the middle ramp, and the red ones are the full ruptures, the purple ones are the partial ruptures, and the blue one is the Gorkha-like event that I compared with the coseismic geodetic data. And the first thing that we see, it looks fairly periodic, right? All the big ruptures are every 1,003. The recurrence time of these big ruptures are every 1,300 to 1,700 years. All of the partial ruptures are basically very similar size and extent, and all of them start from this down dip transition zone, which also is close to the fault bend here. So now to look closely into the seismic cycle with the middle ramp. So you can see these dashed lines are where the fault bends are. So this is the middle ramp. And so you can easily see from this that the presence of the middle ramp sort of affects several interconnected aspects of the seismic cycle. First thing is, if the middle ramp is a geometric barrier that only stops ruptures, then all the partial ruptures would stop before it reaches the middle ramp. But then that doesn't happen. You have some ruptures that break the middle ramp, or even sometimes extend beyond the middle ramp, right? And so, and also you can have these ramp spanning partial ruptures too. So you can see a lot of middle ramp seismicity too. So now if you look at the shear stress accumulation on this fault, it really lights up. So you have residuals from previous ruptures. We have the down dip interseismic loading region, but also all the fault bends create this red region. So we think that this is why we had aftershocks following the Gorkha earthquake in the up-dip region. So I'm going to get to it quickly, but before that, let's look at the time evolution of slip with the middle ramp. You can see that now supercycles are no longer periodic. So it can range from 900 years. This is about 900 years, and that's about 2,000 years. So there's almost thrice the variability in these earthquake cycle characteristics when we go from very periodic giant ruptures to very aperiodic chaotic cycles. We have partial ruptures of varying sizes and extent. And also the hypercenter locations are not, so you have variability in hypercenter locations too. So they're not all from the down dip region. You can also have ruptures that begin and end in the shallower regions too. But this is actually one of the most exciting, for me, exciting part of the result is basically, this is data from Shenji's paper on the double ramp seismicity. And the Gorkha earthquake happened. And then 12 hours following that earthquake, there were a lot of aftershocks which they published. And the ones that I highlight here actually happened up dip of the coseismic rupture, which is where the middle ramp exists. These three panels are from my model with the middle ramp. I've plotted these three observation points. A, B, and C are on the middle ramp, and D and E are on the flat portion, which is where the Gorkha earthquake happened. And I plotted the evolution of peak slip velocity at these observation points. And you can see from the model, there was an up dip aftershock roughly about 14 hours after my main shock, just like what happened after the Gorkha earthquake. Again, I'm not able to reproduce the ridge scenario of the plenty of aftershocks surrounding the coseismic region, which is what happens because stress rapidly decays around the coseismic region. So you have aftershocks at the boundary of the coseismic rupture. But ours is a two-dimensional model. So we have computational limitations. So we were only able to reproduce one of these aftershocks, but it's still very exciting. And another way to visualize the difference between these two rupture sequences is to look at the distribution of rupture sizes. So if I've plotted the distribution of rupture sizes in yellow for the one with the middle ramp, model H, and this one is without the ramp in the middle, model E. And this is the cumulative histogram of all the events in the catalog, which I ran for like about 45,000 years for these two geometries. And you can see the one with the middle ramp sort of follows a power law distribution spanning 4 orders of magnitude when compared to the more periodic cycle that we got without the middle ramp. So sort of circling back and trying to see if we managed to answer some of the questions that we asked ourselves. What controls earthquake segmentation? I think the impact of fault geometry is so multifaceted. There's frictional control, geometry control. It's really very, very hard to sort of deconvolve them and sort of say, this is what geometry does, or this is what friction does. But we saw that fault bends impose a very complex footprint on the megathrust seismic cycle. So what is the role of fault bends? We saw that a middle ramp in the middle of in the seismogenic zone, we need that to explain consistently explain both the coseismic rupture as well as the immediate up-dip aftershocks. And the complexity of all these stress interactions due to these structural gradients translates to a wider range of rupture sizes and extent. And what are the future seismic hazards? So the different scenarios that we can think of following this Gorkha earthquake is, one, it can repeat the 2015 event, right? So a partial rupture that breaks only the lower edge of the lock region, or it could rupture just the unruptured part of the seismic gap, which is the up-dip portion. So you can have an isolated partial rupture just of the up-dip part, or it can be a single megathrust rupture that unzips the entire fault. So to sort of answer that question, I've plotted here the slip that is accumulated on the fault against the down dip distance. So the color again is the fault slip rate. So red regions are earthquakes, yellow is after slip, and the light blue is creep. The black contours are coseismic slip values that are plotted every 5 seconds, and the white contours are cumulative aseismic creep that's plotted every 50 years. And then you can see that both models, so both with model E and model H, what happens is when you've brought the stress all the way to the front, the shallowest part of the fault only ruptures in big earthquakes. So it looks like an isolated shallow rupture is sort of unlikely based on the assumptions of the model. So in both models, we don't see shallow isolated ruptures of the partial region. As the very last slide, I would like to say that we're still missing a lot of pieces of this puzzle. There are a lot of questions that still remain sort of unanswered. And so to take this study forward, you need to sort of include the effect of folding and off-fault deformation. And like I said, this is a 2D model. So we want to see how this sort of segment interacts with other segments along strike, and also look at what is the effect of topography on the seismic cycle. So